So now we're going to look at cost functions, but it helps to first recap the learning diagram. I'm going to say that we're going to start out with some unknown target function that we're trying to figure out. And we're going to see it through the lens of particular training examples, right? So these are the observations, for example, historical records of credit customers' applications. And we have a hypothesis set that's limited by the particular learning algorithm that we're picking here. For example, a linear classifier that can only draw hyperplanes. We're going to tune the parameters of this learning algorithms. These parameters are theta in such a way that we're going to get out a hypothesis H of theta that best approximates F. So how do we get these training examples actually? They come from a data source, right? We have this unknown target function, but it doesn't go through all of the different types of inputs in scriptx equally. Some of the data might be more likely than others. You can think of this as the marginal probability from naive Bayes, but really it's a prior unconditional probability of the types of data we might observe that we need to classify. These data points are going to inform which training examples we can sample from the data. Some points may be more likely and some points will be less likely. All right, so let's take a look at the topic of cost functions. What do we mean when we say a hypothesis approximates F well? It means that we've chosen our parameters theta in such a way that we think is going to match F pretty well compared to other choices. And to do that, we're going to need the notion of a cost function. Our cost function is going to be also known as an error measure, which you'll see in other literature. This cost function is, for historical reasons, denoted as J, to denote the Jacobian. The Jacobian is basically a partial differentiation of this function that allows us to use gradient methods or a generalization of slopes to try to optimize the values of theta. And even though we're using capital J to denote the cost function, usually what we want to do is do some type of aggregate over a pointwise definition. That is, to look at the particular distance or cost between a particular predicted value of x, given our hypothesis, and the true value as coming from f of x. So we're going to aggregate all of these pointwise definitions to create our cost function as a whole. And examples that we've seen are squared error, which we have a squaring of the distance, or L2 metric, as well as a binary classification error, where again, we're using these square brackets to denote whether the statement inside has a true value or not, right? Here, we're going to say that we have an error when the internal part is equal to 1, meaning that the prediction does not equal the actual value. So it should be very clear which one of these is for classification and which one is for regression. Okay, so what we want to do is build from a pointwise error to the overall cost. We're going to see how that works really simply here. Let's take a look at this part here, which indicates that we have a cost function for an individual point, right? We have, after training, the classifier's predicted value and the actual true value as provided in the training example. And whatever type of error function, whether it's a binary error or a regression error, we're going to get a value for this, okay, in this expression. And we're just simply going to sum over all of the instances here. So I'm going to be careful and tell you that we've overloaded the syntax here. The blue J's, the ones here, here, and here, are talking about specific instances within the data set, right? And we're using the function J over here, okay, to denote the cost function that we're going to use. So we're going to use pointwise cost function and aggregate over all of the examples and divide through to get an average. So I'd like you to think about, why do we use an average instead of a sum? Okay, so now let's go to the testing case. And we're going to get the same cost as we saw before, But we don't know exactly which sample we're going to get. So it has to be on the expected X that we're going to get. So again, you can think of the prior probability of the data samples as conforming to some probability distribution, where some of the testing examples may be more likely than others. We're just going to try to find the expected value of the error over all the possible X that we would get from sampling the probability distribution. We've already seen two types of cost functions, binary error and squared error. But many times in a specific domain, we can find that the domain can tell us what type of cost function to engineer, even in the case of something as simple as binary classification. Let's take the case of sickness. We might build a classifier to predict whether you're sick or not, where a positive case is when you're sick and a negative case is when you're well. In this case, we can have two different types of mistakes. We can have the case where there's a false accept or false positive, meaning that the classifier falsely predicted that you were actually sick, but you were actually well, right? A negative case, right? And in the converse, you could also have a false reject or false negative mistake, where the classifier incorrectly thinks that you are well, right? But in actuality, you are sick. So we can take a look at this confusion matrix diagram that's written down here at the bottom to visualize this, right? A false accept is the case where the classifier incorrectly predicts that you were sick, but in fact you were actually well. And the converse case is a false reject, right? Which means that the classifier incorrectly predicted you were well, but you were actually sick. Of course, there's the two cases in which the system accurately predicts the ground truth, or F, where there's no error. When you're sick and the classifier thinks you're sick, and when you're well and the classifier thinks you're well. So given that there's two different types of mistakes that we can make, how should we penalize each of these two cases? Well, it turns out being sick is not so easy because there are different cases in which a sickness can occur. Let's say you're taking your last final exam before graduation, and we ask a question of whether you're sick or not. Well, if the classifier makes a false reject, meaning that the classifier thinks that you are well, but you're actually sick, you get better on your own, right? And you're able to actually take the tests, but you're feeling a little queasy, but you graduate on time. And you might not get the best grades. After all, you're sick. But the case of whether the system actually predicts that you're sick, but you're actually well, you decide not to take the exam, but you have to take the exam next year and possibly pay tuition fees and graduate a year later. That's pretty expensive. So we're going to say that we want to penalize that type of error a lot more. So we're going to give it a weight of 100. What about in the case where there's swine fever? So just in the news recently in Hong Kong, there's this problem that certain people are affected with swine fever, and it's highly contagious. We might ask ourselves again, are you sick? In this case, a false reject is highly costly. If the classifier incorrectly tells you you're well, but you were actually sick, we're going to come up with a case where you are let out of the clinic and you can go on your way and infect many people, causing an epidemic. On the other hand, if you're well and the classifier incorrectly predicts that you're sick, well, that's not so great. You're going to be quarantined for a while, just like if you come out of the airplane and you're sick. It's going to require some inconvenience, but at least you don't get the whole population sick. So we've seen that how you measure matters. When you have a cost function, you should try to fit it to the task as specified by the user or the domain. But in some cases, that's not always possible. Then we might try to use some generic cost function that may satisfy one of two criteria, either a plausible measure, meaning something like squared error, which is simply the case where we might have our observations, our x's, affected by some type of white or Gaussian noise source, or some type of convenient measure. And by convenient measure, we could find some way of making clear that we can have some method for doing some optimization to find the solution quickly. It could be in the form of a closed form solution or something that aids convex optimization. So let's summarize what we mean by cost functions by looking at the learning diagram again. So now we have the testing data as we talked about in the previous part, and we want to aggregate the pointwise error in this learning diagram. Where would we place it? In fact, it goes here, right? Between the learning algorithm, because we're going to use the cost function to tune the parameters, and the data source to compile what the final cost is when we come up with a hypothesis function. So in summary, we've seen that cost functions are application specific where possible, and that you should try to specify what the costs are because different types of errors may have different costs. And false accepts and false rejects may differ in the amount of badness that they create for the system.